Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today we have two very special guests talking about innovation and the future of progress and technology. You know, just last month, there was a major report coming out stating that American students, once again, score near dead last among students in the industrialized world. In fact, our students, compared to students from Jordan, scored just a little bit better in terms of math and different kinds of reasoning skills. Now, the report had a summary, and the report said that this is unsustainable. I mean, how can you have a great industrial power which graduates students which simply cannot cut the mustard in the new technological age? Now, of course, there's unemployment in the world today. Everybody knows that. However, did you also know that there are plenty of jobs out there, unfilled jobs, jobs that are just begging to be filled, high-paying jobs, but unfortunately, there are not enough American students to fill those jobs. In fact, this report says that there's actually been a decline of the cognitive skills of our students compared to the past, and especially compared to students in China and India and throughout the developing world. Well, that's why in this hour, we're going to talk about invention, innovation, science. Science is the engine of prosperity. All the wealth we see around us, yes, it comes from labor, it comes from hard work, it comes from entrepreneurs, it comes from visionaries, industrialists, government policy, and all that. However, ultimately, after everything is said and done, science is the engine of prosperity. And the question is, will we continue to graduate young kids that can keep us at the forefront of innovation and wealth and prosperity? Well, we have two very special guests today. The first special guest is Randall Strauss, who recently wrote a biography of the greatest innovator of modern times, Thomas Edison. We forget that Thomas Edison pretty much created the 20th century in terms of household appliances, in terms of power, in terms of entertainment. And it's something that we should emulate. It's something that we should try to learn. How was it that Thomas Edison, who came out as practically a penniless kid, could achieve so much in his lifetime? And then the second half of Exploration, we're going to bring on somebody who's at the forefront of innovation itself, MIT professor Seth Lloyd, who is pioneering something called quantum computers, which some people think could be the new technology of the 21st century. Now, of course, there are a lot of hurdles that have to be negotiated before we have commercial quantum computers, but once we do, perhaps sometime in this century, it could create a second industrial revolution. Quantum computers can leave ordinary computers in the dust. Not to mention the fact that ordinary computers are beginning to flatten out now. Moore's law, which says a computer power doubles every 18 months, is slowing down. And we need something like atomic computers, molecular computers, quantum computers to save the day. Well, once again, our first special guest is Randall Strauss, author of a biography of Thomas Edison. And the question is, what makes a great innovator? And now I'd like to introduce our special guest for today. He's Randall Strauss, a columnist for the New York Times, and he's written a delightful new book called The Wizard of Menlo Park, How Thomas Alva Edison Invented the Modern World. That's right, invented the modern world. We're talking about the man who invented the phonograph, invented the light bulb, invented the motion picture industry, invented the electric power grid, and most of what we today take for granted as the modern world. And the question is, what was the secret of his success? And if you are an entrepreneur, especially in Silicon Valley, what kinds of traits can you learn? What kind of tips can you learn by studying the life and the mistakes of the Wizard of Menlo Park? So once again, our special guest today is Randall Strauss. The book is called The Wizard of Menlo Park, and he's a columnist for the New York Times. The first question for you is, how did you get interested in writing a biography of this iconic figure, Thomas Edison?
About 10 years ago, I wrote a biography of Steve Jobs. I was looking at Jobs' attempt to found a second company after Apple, and he was a big fan of Edison. And in the course of doing research for that book, I kept running into Edison's name, and then the book that followed that, which was about Bill Gates and Microsoft, again, I ran into Mr. Edison. I think it's fair to say that anyone working in the high-tech industry today owes a lot to Edison, and many people feel that connection, that debt to the inventor's contributions that set up the infrastructure and also set up a model of the inventor slash business person, the tech-savvy entrepreneur.
And
so
also,
he served as an inspirational example for today's successful entrepreneurs. Yeah.
Okay. And, well, let's talk about his early years. Of course, he wasn't born rich. He didn't have scientists, professors as parents, and yet he's a self-made man that changed the world. So what about his early years?
He received virtually no formal schooling. He was homeschooled for a few years by his mother, but not for very long, and was selling fruit and snacks on a train as a very young boy. And he was self-taught. And I think one reason we have long been curious about his earliest years is because he was really the last, you might say, the last prominent figure in a technical field who could get away with absolutely no formal schooling. In a way, he was an exception then, and he has remained a curious figure. It's as if the more formal training that is needed in a given scientific or technical field, the more interesting the Edison counterexample is.
I guess he shares some similarity with a Michael Faraday of England, who was also self-taught and born into poverty, was a bookbinder, and became one of the greatest scientists of the 1800s. So I guess there's some similarity there, except that Michael Faraday is on, I think, the 5-pound note. He's on the British money, but Edison is not on our money.
He is not. It's interesting. He had 6 children, and 2 of them went to MIT. One did not complete his degree, but his very youngest son, Theodore, did complete his degree and actually did some graduate work. And it's interesting, the contrast between the formal training that the father received compared with his youngest son. So in the course of 2 generations, we see a change, a very dramatic change in what is necessary for being educationally equipped to create new things.
Okay, well, let's talk about his first great invention, which we take for granted. But if you could tell us a little bit about the shock that people felt when Edison invented the phonograph.
It did come as a shock, and we've lost that sense of awe that was present when the very first witnesses to this miracle heard it for the first time. Part of the shock was the physical dimensions. It was a small device. Essentially, it was a cylinder that was mounted with a crank, and a sheet of tinfoil was wrapped around it, and a stylus was placed on top, and the stylus was connected to a very, very crude device, essentially a microphone. And at the time, others had tried to recreate human speech by means of building machines that were closer to a pipe organ than anything else. They were large. They involved bellows. And here was this device that fit literally on a tabletop. There was not much to it, and that it could faithfully reproduce any human sound in any language. That was also very impressive to those early observers. Was something that no one before its invention literally had even conceived of, let alone imagined it would be possible to build.
Now, in your book, you detail how shocking it was, headlines stating that you could finally hear the voices of dead people. You could record the voices of your father, your mother, Caruso, great politicians, and actually hear their voices after they're dead. That was stunning, right?
The idea was stunning, but let's remember there were no voices to be played initially. And in fact, that early demonstration phonograph was not really a practical machine. I mentioned it took you would wrap a sheet of tinfoil around it. What those witnesses who spoke excitedly about being able to hear dead poets in the future didn't realize was that once you took that sheet of foil off the machine, you could not put it back on and play. And all the demonstrations of the phonograph those early years involved Edison or his assistant recording and then instantly playing without touching that tin foil. And it would only be when he develops, he and his competitors, first a wax cylinder and then a disc, was the recording medium sufficiently durable to permit a separation of recording and playback.
Okay, now we'll talk about fame a little bit later because he becomes increasingly famous over the decades. But what was the reaction to this machine and the reaction of this man who performs this miracle of recording the human voice for the first time?
Well, part of the surprise was that the inventor was a young man. He was 30 years old. And he very shrewdly decided to unveil his machine in the offices of Scientific American. He takes the machine into the office, puts it on the table, and he has pre-recorded a self-introduction. So the phonograph says to the gathered editors, "Hello, I'm the phonograph." And it was stunning. And Scientific American literally stopped the presses. They had an issue that was in production at the time. The editors decided on the spot to hold that issue and insert notice of this wondrous invention. And that moment made Thomas Edison famous. When the phonograph is announced with the imprimatur of the Scientific American's editors behind it, it had instant credibility, and he became famous at that moment and would learn that once you achieve the kind of fame he was given, he could never become anything but the famous person. He couldn't turn off the fame. He could never become unfamous.
What do you mean by that? People chasing him for autographs or spying on him and looking at his garbage? Or what do you mean by that?
Well, he did not face quite the intrusiveness that celebrities today face, but it was pretty close. The world, first of all, when it becomes aware of his lab in what was then rural, suburban New Jersey, becomes aware of his laboratory, they descend upon it, and they think nothing of interrupting his work. And there's a time when he was unable to get much of anything done because visitors would come in and demand that he play for them a demonstration song, and the song that Edison was condemned to repeat again and again and again was "Mary Had a Little Lamb." This was the price of fame. Fame got him a contract with investors to establish a company that was going to commercialize the phonograph, but fame at the same time brought a torrent of visitors, a torrent of mail. The mail would include a category of requests that he termed begging letters. Strangers would write him saying, "I need money," something I think famous people today would recognize as a phenomenon that persists today.
In fact, if you win the lottery, that's the first thing that happens, right? You get deluged by people who have their hands out.
And what I find is very interesting in looking at Edison's acquaintance with fame and the price it exacts is how the public has no compunction about respecting the privacy of the other person. Just incredible demands are made upon Edison, and at first he doesn't realize how big a burden it's going to be for him, for his family, and his children are going to always live in his shadow. So they're going to pay a price too.
Okay. Well, let's move on because Edison tops this. Not only is he now world-renowned, he goes on to invent the light bulb and the motion picture industry. So could you walk us through his succeeding inventions?
The phonograph comes when he's 30, and by the time he's 35, he's going to have announced that he's solved the problem of what was then called subdividing light, that is, coming up with a workable incandescent light bulb. At the time, arc lighting was dominating cities, and it was too bright for indoor use. He's going to announce he's invented it before he has. Then he's going to scramble to come up with solutions to problems he ran into in the course of trying to come up with the incandescent light bulb.
Mm-hmm.
Then he's going to form a company, land permission to build the first central power station that supplies indoor lighting system in Lower Manhattan.
That was on Pearl Street, right?
On Pearl Street, right.
Mm-hmm.
And he's going to succeed. When he turns the switch, it works. He's going to do all of this. So from phonograph to successful build-out of the first municipal incandescent lighting system and accompanying power infrastructure.
Okay, now
do all this in 5 years. Amazing.
Now, when I was a kid, I read a biography of Thomas Edison, and there's a famous story of how he would experiment with literally hundreds of different kinds of substances that would incondense in a light bulb to create the light bulb. And that became legendary. And there's that famous quotation that genius is, 99% perspiration, 1% inspiration. How much of that story is true?
Well, let's start with that famous quote. It turns out I could find no documented evidence that he ever said that. If you track down the source that was used by earlier biographers, it turns out it's a phrase used by someone who claimed acquaintance with Edison, who was speaking it several decades after he claimed he had heard Edison use the phrase. But there's no, certainly there is no document in Edison's own hand where he uses this.
Now, what about the story, though? The story, though, that he went through hundreds of substances before he finally got it right.
The story is true. They did go, and I'm using the plural, they. It was he and his assistants. And part of the problem with the myth of the lone, inspired, hardworking inventor, the outsized image of Edison, the inventor, was he always, from very early on, even before, of course, the invention of the phonograph, he had a team of assistants. So it wasn't Edison alone. It was the assistants who were running through long lists of all kinds of materials to see what would serve well, what would last as a suitable filament. They had a lot of fun with this, too, just trying outlandish materials to see what would work. And it would be a strip of bamboo that would turn out to be the basis for the first generation of really workable incandescent bulbs. The other thing about this story that I think is interesting to look back on was how it was not informed by scientific theory. At the time, it was termed cut and try. That is, just try everything. Today, we would more colloquially say throw some stuff against the wall and see what sticks. And that really was the technique. And of course, this approach, this methodology, if I can dignify it with the term methodology, it's really the absence of a methodology, is not going to be a serviceable model for the institutionalization of invention that's going to follow Edison's career. He's going to be the one who makes this an appealing kind of storybook approach to invention, but it's not an approach that corporations are going to copy as they institutionalize invention.
Okay, let me ask you about a famous story about Edison. He was suspicious of people with fancy degrees from colleges. He was going to hire, according to the story, this one PhD, and he asked him to calculate the volume inside a light bulb. Okay, so this PhD candidate got out and used calculus, and after many hours, came out with a number that approximated the volume inside a light bulb. And then Edison simply got the light bulb, put it under a faucet, put water in the faucet, and then simply weighed the water and got the calculation within a matter of seconds, just to prove that you don't need so much book learning. Is that really true?
It's a true story. I saw several different accounts of it. It involved actually an employee of his, and you have to feel sorry for the PhD who was hired for his training, but was subject to really what were cruel pranks. Edison felt so ambivalent about those who had received, who had graduate degrees, who had received advanced training. He couldn't resist looking for opportunities to humiliate his most highly trained staff. And that's a great example of this ambivalence.
Okay, now tell us a little bit about the motion picture industry.
Motion pictures are going to be a passion of his. He works on a camera that is going to advance the field. He's going to buy the rights to use a projecting system that really makes possible the ability of audiences to see motion pictures on a screen. He was not able to invent that himself, and he and his advisors were willing to acquire the technology and market it under his name. He understood that he had acquired a reputation that had commercial value, and just the association of his name made this technology viable. It was an incredibly competitive marketplace. There were a number of competing projection systems that were all jostling with one another. He was also involved in the production of movies. He had a movie studio, and under his name, a number of very important early movies, very short movies, were made until he did eventually leave the business. he, in movies as in recorded sound, enjoyed the privilege of making artistic decisions about what would get produced, what kind of movies, what kind of musicians would receive his support. And so we have the case of an inventor wielding power into in the artistic realm, and he enjoyed that role very much.
Okay, let me ask you the key question then. What was the secret of his genius? Was it that he was born that way? Was it that he simply tried everything under the sun until he got it right? What was the secret of his genius that, of course, Silicon Valley entrepreneurs today try to emulate?
He's certainly a serial entrepreneur, and he was very gifted with, in a technical sense, of being able to identify the crux of a technical problem, being able to guide his assistants in the search for a solution. And in our memory of the Edison legend, just as is the case today in Silicon Valley, we do remember the successes, and we are inclined to forget the failures. Steve Jobs is a great example. I mentioned I'd written a book about his career when he started this second company. I would imagine most people certainly know of his recent successes as well as his early successes, but probably don't remember there was this interval of about 10 years where he tried to start and failed in making a new company that offered a workstation, high-end computer for a academic market. And so, too, in the case of Edison's career, there are times when he tries something and fails utterly. The most dramatic example was when he left the electric light and power business and basically liquidated his stock that he received in the creation of what's going to become General Electric, and puts virtually all of his money into iron ore mining in a venture that did not work out. That's part of being a serial entrepreneur. You will succeed, but not always. So I don't think that detracts from his successes. And some of his failures were glorious failures. We can talk about the electric car as what I think of as one of his glorious failures.
Well, that concludes our interview with Randall Strauss, author of a new book about Thomas Edison. And stay tuned for the second half of Exploration when we talk about the next generation of innovators. And the question is, what can we learn about the spirit of creativity, innovation that will create wealth into the future? Think of the enormous wealth generated by the light bulb and by the work of Thomas Edison. And the question is, are we up to the task? Can we create the next generation of Thomas Edisons? Well, that concludes the first part of Exploration. Stay tuned now for the second part, when we talk about perhaps where some of the next innovations may come from. New advances in computers like molecular computers and even quantum computers. Our next guest is an MIT professor, Professor Seth Lloyd, who'll talk to us today about quantum computers, which, if we can harness the power, could initiate a second industrial revolution. We're talking about a generation of computers that would leave the old computers in the dust. So once again, stay tuned for the second half of Exploration as we continue a discussion of innovation in the 21st century. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. introducing the second half of Exploration. In the first half of Exploration, we mentioned that our students score near dead last among industrialized nations in terms of competency in math and reasoning skills, and this has been pretty much consistent over the last decade, so it's not a spurious effect. And the question is, if science is ultimately the engine of prosperity, then where will the next Thomas Edisons come from? You know, if you look at the political debate in this country, it's mired in politics. First of all, politicians are former lawyers. And in law, you have this worldview that the universe is a zero-sum game. The basis of law is you sue Peter to pay Paul. Well, when these lawyers become politicians, they bring this worldview with them, this zero-sum game. Instead of suing Peter to pay Paul, you basically tax Peter to pay Paul. And if you listen to the political debate, it's very sad because all they do is cut the pie thinner and thinner and thinner. Who are we going to rob to pay Paul? Who are we going to tax? It's all tax policy. But you see, a physicist has a different point of view. We believe in creating a bigger pie. Rather than slicing the pie thinner and thinner, rather than robbing Peter to pay Paul, why not create new industries? Think of two simple inventions from quantum physics. Quantum physics is my specialty. That's what I do for a living. That's my day job. And in quantum physics, we have two simple inventions that changed everything, the laser and the transistor. Think for a moment. Most of the high-tech innovations have been due to these two very simple inventions from quantum physics, the laser and the transistor. Computers, the internet, iPods, iPads, MRI scans, modern medicine, the space program, GPS, all of that is possible because of innovations coming from quantum physics. And the question is, where will the next Thomas Edisons come from? Some people think that maybe, just maybe, it could come from a new generation of computers, for example, quantum computers. And then we're going to bring on our second special guest today. He's a professor of physics at MIT, Professor Seth Lloyd, who believes in quantum computers. The age of silicon may eventually come to a close, and then we may have to go to quantum computers or molecular computers and realize that some people even think that maybe the universe is a quantum computer of some sort. So now in the second half of Exploration, we'll talk about where the next wave of innovation and wealth will come from. And now I'd like to introduce our special guest for today. We're very delighted to have with us Professor Seth Lloyd of MIT, author of a new controversial book called Programming the Universe. And the question is the universe a quantum computer? Now, let me explain. We all know that computers that energize modern society are based on silicon. And the silicon chip that you have in your Pentium crams literally millions upon millions of tiny transistors into something that's a little bit bigger than your thumbnail. And the question is, how far can you go until the tiniest transistor becomes the size of an atom? Well, that time is coming. Perhaps in 20, 30 years, we don't know precisely when, but we do know that someday transistors will be so tiny that atoms of silicon simply won't do. We'll have to go to atomic computers, otherwise known as quantum computers, and Professor Lloyd is an expert in this area called quantum computation, and he thinks maybe even the universe is a quantum computer. Now let me also note that atoms spin like a spinning top, and you all know that spinning tops have an arrow, the axis of spin, and that could point up or down. If it points up, that's a 0. If it points down, that's a 1, and you get binary. But atoms are more than just binary. Atoms can also point sideways and everywhere in between, a superposition of up and down. And that's where we get into the bizarre world of the quantum theory, where you don't really know quite where this arrow is pointing, but you have much more freedom than simply zeros and ones. You have zeros and ones and in between. These are called qubits or quantum bits. And Dr. Seth Lloyd is one of the world's experts in this new area. And of course, many people are interested in this. Modern technocrats are interested because one day quantum computers may have the internet on it, and as well as banking records and your credit card records, not to mention the fact that the CIA wants to get their handle on quantum computers because with it, you can crack any code with a quantum computer. So once again, our special guest today is Dr. Seth Lloyd, author of the new book, Programming the Universe. Professor Lloyd, tell us a little bit about your youth. Were there any kinds of incidences or stories you'd like to tell about what set you off in a career in mathematics, computational physics, and physics?
Well, I always loved fooling around with numbers and with games and things involving geometry when I was a kid. I played a lot with blocks and would build huge geometric constructions as well as buildings with them. And then when I went to school, I was amazed to find out that there was a subject called physics where with relatively simple math, you could discover a huge amount about the way the world works. Of course, then I went to graduate school and found it was really the opposite. There's a huge amount of complicated math, and you only understand a little tiny bit about the way the world works. But by then it was too late. I was suckered into the field.
And you also mentioned in your book that as a graduate student, everyone seemed to be doing string theory, but you saw your destiny going in a slightly different direction. Could you elaborate?
Sure. When I was at Cambridge University, I did a MPhil in History and Philosophy of Science and started working on ideas of information and quantum mechanics. I also studied quantum gravity with Stephen Hawking. And it struck me that there was a connection between these two things, these two ideas of quantum information and quantum gravity. So when I went to Rockefeller University to work with Heinz Pagels to do a PhD in physics, I started off working on ideas of quantum information and quantum gravity, basically the same thing that I'm doing today. Unfortunately, they didn't like that very much at Rockefeller University, and about halfway through they told me I better cut it out and work on something more conventional like elementary particle physics or string theory.
Well, I guess reality intrudes. And Heinz Pagels, I should also mention, was one of the early guests on Exploration, speaking about elementary particle physics. Now let's talk about things that are very practical. The average American, of course, says, what's in it for me? Numero uno. Am I going to get better internet reception? Am I going to get better computer power? So let's talk about computer power, computer games, and what we have for Christmas. Everybody knows that at Christmas time, your computer is almost twice as powerful as the computers of the previous Christmas. And that's called Moore's Law. So some people say, well, Moore's Law is going to go on forever. However, you think otherwise. So tell us a little bit about Moore's Law and why you think Moore's Law is going to break down. So by Christmas time, we're not going to get Christmas presents that are almost twice as powerful as the previous Christmas.
Well, it's dangerous to predict that Moore's Law will break down. People have been predicting its imminent demise for decades, starting in the late 1960s. And every time some clever engineer managed to find a way around whatever specific problem seemed to be standing in the way of progress. And in fact, if you look at Moore's Law, it's not just one technology that has made computers get more powerful by a factor of 2 every year and a half or so. It's a whole series of technologies that have kicked in, from vacuum tubes to transistors to integrated circuits. And these technologies rely on the improvement, the rapid improvement of other kinds of methods like machining, material science, etc. So Moore's Law is kind of the tip of the iceberg of this rapid improvement. However, it can't actually go on forever for a simple reason, that is that computers are governed by the laws of physics. And the laws of physics tell you how small you can make things and how fast you can do things. And so if you actually took all the energy in the universe and turned it into a gigantic computer, a possibility envisaged by Isaac Asimov in his story, The Last Question, I was able to calculate using the physics of information processing how big such a computer would be. And, this computer, this universal computer, if you like, up till now it could have performed about 10 to the 120 elementary operations, or ops, on about 10 to the 90 bits. And if you actually look at the exponential progress of Moore's law and ask at what point could the whole universe become a computer, it's only 250 or 400 years away. So even if we manage to take every elementary particle in the universe and turn it into have it participate in a computation, then Moore's law couldn't last for more than a few more centuries.
Okay, well, let's be very practical. On your desk is a laptop with a Pentium chip, let's say, and that Pentium chip has a layer of chemicals, the smallest layer being 20 atoms across. 20 atoms across, the smallest layer in a Pentium chip on your desk. In 20 years, in fact, less than 20 years, that layer will be 5 atoms across at the rate at which we're going. 5 atoms across. And at 5 atoms, we have to introduce something called the Heisenberg uncertainty principle, which says you don't really know precisely where that electron is. In which case, if electrons leak out of the layer, your Pentium chip just short-circuited, and your laptop is now useless. And so the question is, how small can you make a transistor before you bump up against atoms, and at the atomic level, everything's uncertain?
Yeah, well, that certainly is something to worry about. And indeed, if Intel starts making chips where the electrons are just leaking out all over the place, the chips wouldn't work. So they clearly can't make them by exactly the same design. However, there's certainly nothing wrong with, or nothing against the laws of physics to actually store bits of information at the atomic scale. Indeed, 1 atom, 1 bit. And as the components of computers get smaller, indeed, quantum effects like the Heisenberg uncertainty kick in. But maybe we can actually take advantage of these effects like the Heisenberg uncertainty principle. Maybe we can turn it from being a bug into a feature. And indeed, that's what my colleagues and I do when we try to build computers whose feature scale, the size of the bits, are down at the level of individual atoms.
Okay, now let's talk again very practical things when people say, what's in it for me? Well, the government, of course, would ask the same question, what's in it for us? And let's not talk about the CIA. The CIA, of course, is very much interested in breaking codes. They love to break the codes of other nations. But many times to break a code, you have to have a key. And sometimes this key is the ability to factorize a huge number. Let's say I have a number with 100 digits. Take a sheet of paper and write a random set of integers 100 digits long, would fill up many, many sheets of paper. And then you were asked to factorize it as the product of 2 numbers. Well, how would you do that? It would exhaust most computers, and some people therefore think that certain codes are safe, that it's beyond the ability of most ordinary computers to crack the factorization of a number that is 100 digits long. But now let's talk about computing atoms. Is it possible that this new generation of computers, this quantum computers that you are pioneering, could be able to crack codes that even the CIA cannot crack?
Well, it's possible, and indeed, if we could build a quantum computer, a computer that stored bits of information on individual atoms, one with only a few tens of thousands of quantum bits, and one able to perform a few 100 million operations, which is to say something quite piddling compared with the laptop on my lap right now. If we could build a very small quantum computer, then we could use these kind of weird features like the Heisenberg uncertainty principle to compute in a different way. And indeed, in 1994, Peter Shor then at AT&T, now at MIT, showed that, in fact, you could exploit quantum weirdness to factor large numbers and break these codes with even a rather small quantum computer.
Okay, now let's talk about computers themselves. Everyone talks about the digital age. Everything is digital. But what does digital mean? And what is this zeros and ones that sometimes we see in the press? And like if you saw the movie The Matrix, you saw a bunch of zeros and ones. What are these zeros and ones? And what is the so-called digital age?
So a 0 or 1 is what's called a bit. A bit is the smallest possible chunk of information. And it doesn't have to be 0 and 1. The famous bits are yes or no, heads or tails, true or false, black or white. Essentially, any thing that can take on two different states, two different distinguishable states, registers a bit. And that's the smallest chunk of information. And the way that digital computers work is they break up information into bits, into its smallest chunks, and then process it that way.
Okay, so if modern society, the wealth of nations, everything we see around us, if it's governed by zeros and ones, then let's now talk about qubits, quantum bits, where atoms don't have to be in zeros and one states. They could be zeros and ones and in between. So tell us about how atoms can be in between 0 and 1.
Yeah, well, as soon as one starts talking about quantum mechanics, then things start to get weird. Niels Bohr famously said that anyone who can contemplate quantum mechanics without getting dizzy hasn't properly understood it. But let's go on anyway. Back essentially a little more than 100 years ago, physicists including Max Planck, Einstein, Niels Bohr, and others realized that there was an essential chunkiness to nature, a kind of a digital quality, that things that people thought of as being wave-like, like, for instance, light or sound, came in little chunks. Light came in little chunks called photons, a little particle of light. Sound came in little chunks called phonons, a little particle of sound. And so at this quantum level, things that look continuous actually are somewhat digital. For instance, you could have no photons in a spot or one photon in a spot. Or you could have one electron over here or one electron over there. And indeed, that's how a conventional computer registers bits, so with a lot more electrons. So, bucket empty, lots of electrons out of the bucket, that's 0. Bucket full, lots of electrons in the bucket, that's 1. Now, in quantum mechanics, so quantum mechanics says the at bottom of the world has this digital feature, which is good because that means we can use this digital nature of the world, this quantum nature, to store digital information. But there's another weird feature of quantum mechanics that goes under the name wave-particle duality. So just as waves like light are made up of particles, so things like particles, like electrons, for instance, have waves associated with them. The wave is, an electron's wave tells you something about where the electron is. Now, so in a digital world, an ordinary bit, you could either have an electron here, that's 0, or there, that's 1. But in the quantum world, the electron's wave can be both here and there at the same time. So a quantum bit, electron here and there at the same time, is a bit that can register in some funky quantum sense that nobody really understands, 0 and 1 at the same time. Qubits are not either 0 or 1. They can be 0 and 1.
Okay, so let's take an analogy of a top, a spinning top. Everyone's played with them as children, and atoms spin, and therefore atoms are also like spinning tops, and atoms can spin either up or down when they're placed in a magnetic field, or at least until the quantum theory came in. And so now we can have tops that spin up, tops that spin down, and tops that spin in between. Now, these qubits, these quantum bits, can be between 0 and 1, and they consist of atoms now, not molecules of silicon that you see on a transistor. So how would you actually now build a quantum computer? Let's say that you were an inventor, have access to laser beams and magnetic fields and the ability to play with atoms, individual atoms. How would you build a quantum computer?
So I guess, in fact, a little more than 10 years ago, I was in that position because quantum computers, the idea you could compute at the level of atoms using quantum mechanics, had been proposed by Paul Benioff and Richard Feynman back in the 1980s. But until by the early 1990s, nobody knew how to build one. Nobody had a clue. And around 1992, 1993, I realized that with off-the-shelf elements like lasers and microwave generators, you could take atoms and make them compute. And the way the type of computing I suggested was, in fact, just what you suggested. We'll take spin as our bit. So spinning up, or we can call that clockwise, is a 0, and spinning down is a 1. And then spinning sideways is this funky state of a qubit, 0 and 1 at the same time. So now, if you take such an atom, the spin of the nucleus of an atom, you put the atom in a magnetic field, and then you zap it with microwaves, you can make that bit flip. This is called magnetic resonance. It's the same technique that you use to image your knee when you blow it out while skiing. So if you put on light or microwaves at just the right frequency, it will tickle the nucleus and cause the nucleus to flip. First, it will start at, let's say, it starts at the state 0, or spin up, and then it gradually rotates down through the state spin sideways, 0 and 1 at the same time, to the state spin down, or 1. Now, if you have lots of atoms, lots of nuclei, you can address them with different frequencies. You can think, in fact, of these different atoms as essentially listening to different radio stations. So, if I have one atom that listens to 89.7 megahertz, WGBH here in Boston, then a second one, say the first one is carbon, say the second one is hydrogen, will listen to WCRB, 102.5. And when I address these two atoms with microwaves of different frequencies, radio waves of different frequencies, then if I shine light at 89.7, the carbon atom, which listens to 89.7, will flip. And if I shine light or microwaves at 102.5, then the hydrogen atom, which listens to WCRB, will flip. So I can address atoms individually. And then if you're sensitive to the interaction between the atoms, you can massage those interactions to make up logical operations. For instance, causing the hydrogen atom to flip if and only if the carbon atom is spin down or 1. And since at bottom, a computation is nothing more than making bits flip, and making one bit flip if another bit or several other bits, say, read 1, then any computation can be broken down into these simple operations, making bits flip, making them interact with each other. And the atoms in our molecule, the carbon and the hydrogen, can perform a simple computation simply by addressing them with light.
Okay, so let's back up a bit. You have a bunch of atoms, let's say in a line, and you place it in a magnetic field, so the spins are either up or down, or perhaps sideways, a mixture of up and down. And once you have these atoms aligned, then you hit it with microwaves, and at certain frequencies, the atom will absorb the radiation and flip.
That's right.
And each flipping process represents a calculation. Now, because the atom is neither up nor down, but it's a mixture of up and down, you have much more flexibility than in zeros and ones. Okay? Now, then the question is, what kind of computation can you perform on this? Can you do the calculations of a laptop? Can you do 1 + 1 is 2? What's the world's record for computing on these atoms?
So you can certainly take these atoms and make them do anything that an ordinary digital computer could do. So at the moment, because atoms are very small, and even if you extrapolate Moore's law into the future, depending on how you calculate size, then it will take 25 to 40 years for us to get computers where the components are atomic, even if Moore's law continues at its current breakneck pace. But the quantum computers we've built can do anything that an ordinary computer, say, with 7 to 10 bits can do, because that's the size of the computers we're looking at right now. However, so as viewed as classical computers, just doing ordinary operations like 1 plus 1 equals 2, then they're pretty weak, these quantum computers. Not only are they small in actual size, the size of of a small molecule, but they're small in terms of power. However, if we start to take advantage of the ability of atoms to read 0 and 1 at the same time, then quantum computers can do things that classical computers can't. And the secret comes from looking at what bits can do in a computer. So bits can store data, but they also can be instructions. So 0 can mean do this, right? And 1 is an instruction meaning do that. Now, if I take a quantum bit, a qubit, that reads 0 and 1 at the same time, and I feed it into a quantum computer as an instruction, then the quantum computer will do this and it will do that at the same time. So quantum computers can multitask or do parallel computation in a way that classical computers can't. And that's why if we could build a quantum computer, say, with a few tens of thousands of quantum bits, which is difficult, but certainly not impossible, then we might be able to start striking fear into the hearts of the CIA, the NSA, and other three-letter agencies.
Now, the reality, and correct me if I'm wrong, the reality is that the world's record for a quantum computation is, drumbeat, 3 times 5 equals 15. And I understand that calculation was done on something like 5 to 7 atoms. So correct me if I'm wrong, but at the present time, we're still at doing calculations that even children can do.
Tiny steps for tiny bits, Michio.
Mm-hmm.
You've got to start from somewhere. And indeed, as you pointed out, the whole notion that quantum effects might come into play strikes fear into the heart of Intel. So we have to figure out how to make atoms compute, and before we start to make Avogadro's number of atoms compute. So, starting about 6 or 7 years ago, we started to do the first quantum computations, and we've been gradually making them bigger. It takes a tough engineer to handle a tender atom. Atoms are small and sensitive, and as I say, we're not even due to make atomic scale computers for another 25 to 40 years by Moore's law. So it's hard to do.
Well, that concludes today's program about innovation and imagination, which will drive prosperity into the future. Our first special guest was Randall Strauss, author of a biography of Thomas Edison, the premier inventor of the last century. And the second special guest was Dr. Seth Lloyd, professor of physics at MIT, talking about beyond silicon, that is, quantum computers. And this has been Exploration with Dr. Michio Kaku. And you can get a copy of today's program by calling the Pacifica Program Service at 1-800-735-0230. That's 1-800-735-0230 for a copy of today's program. So, good day. This is Professor Michio Kaku, and this is Exploration.